Now let's talk about the second circuit analysis technique, mesh or say loop analysis. Like I said before, it is an alternative technique to nodal analysis, and both are for finding the voltages and currents everywhere in the given circuit. Well, of course, only one might be asked for, so be careful how to answer your questions in the exam problem. You don't have to find everything, and only one of them is asked for. Alright, let's see how we conduct this mesh or loop analysis. Also following the same pattern and idea, we have two steps. First is applying KVLs this time in mesh or loop. Second, rewrite those voltages in the mesh or loop KVLs in terms of current by, again, applying Ohm's law on the resistors. And now we are watching the exactly same circuit as we used in nodal analysis. Let's see how it works. So again, to write KVLs, we need to identify what meshes or loops we have here. If we pick loops to write KVLs, you should first of all realize we have 3 loops like this. Of course, I'm also assuming a clockwise rotation direction for you to write KVLs. For these 3 loops, the corresponding KVLs should be like this. Okay? For example, in loop 1 here, we have V1 positive negative, followed by VA positive negative, and then followed by 12 volt negative positive. Therefore, we have positive V1 plus positive VA plus negative 12. The total is 0, which is following, obviously, the first statement of writing KVL. Similarly, in loop 2 here, we are coming across V2 first positive negative, and then VB positive negative, and then VA negative positive. So here we go. Positive V2 plus positive VB plus negative VA equals 0. In loop 3, we have, again, positive negative V3, positive negative VC, negative positive VB. So positive V3 plus positive VC, negative VB equals to 0. So 3 KVLs in 3 loops like this. Obviously, by the concept of loops, we have more than these 3. So what are they? First one, we have loops here. We call it number 4. And the corresponding loop equation is positive V1 with this polarity, positive V2, and positive VB, and then go back to negative 12 volts. More loops here. We are having positive V2, positive V3, positive VC, and then go back to here, which is negative VA, or loop 5. And of course, we have a very last loop 6, the biggest one. The corresponding KVL is V1, V2, V3, VC, and negative 12. Sum of them equals 0. So we have up to 6 loops and the corresponding 6 KVLs. Here, the same trick we had in nodal analysis happened here as well. In terms of algebra thing, look at equation 4, 5, and 6. What they are is actually the derived equation out of equation 1, 2, and 3. Therefore, they are not distinct equations and thus useless. How that be? Let's see equation 4 here. The nature of equation 4 is we sum up equation 1 and 2. We come up with equation 4. Equation 5 is the sum of equation 2 and 3. And equation 6 is sum of equation 1 through 3. Therefore, again, they are useless. So now see, we only need to keep loop 1, 2, and 3 KVL's equations. And they are nothing but meshes. Regarding the concepts of mesh and loop, we learned those in module 1 and reviewed here as mesh is the loop contains no other loops. Therefore, 1, 2, 3 here are meshes. But also be careful. the mesh is definitely a loop, one kind of it. However, the loop is not necessarily a mesh. So basically you can see I'm changing the mesh or loop becomes mesh, since only mesh KVLs count for finding the voltages and currents you need in the analysis. Other loops equations are not necessary. With those being said, let's move to the next step, which is rewrite these equations. The reason is very simple. Again, look at these three meshes. V1, VA, V2, VB, V3, VC, we have up to 6 unknowns. However, 3 equations. We can calculate nothing out. So we have to move on to the next step. Rewrite all of these voltages in KVLs in terms of so-called mesh currents by, again, applying Ohm's law. And let's see how it works. So to the first mesh equation, KVL, we take care of V1 first in terms of mesh currents. What it means is, inside of the mesh 1, we are seeing a rotation direction, which is nothing but a current flow direction as well. So we call the current inside of this particular loop as I1. Further, it means we have I1 through 12 volts, I1 through 9 kilo ohm, and I1 through 6 kilo ohm. Be very careful. I1 is not equals to this current of this branch. So based on this idea, V1 is equals to, by Ohm's law, equals to I1 times 9 kilo ohm. Because V1's voltage polarity is like this, and the I1 current direction is entering the positive polarity. Therefore, it's consistent with the passive sign convention. Therefore, we don't have a negative sign in front of it. Okay, be very careful. Next, we need to take care of the voltage cross 6 kilo ohm, which is VA, second voltage term in this equation. It equals to what? This is a little bit tricky. You need to be very, very careful. This involves the current in the mesh 2. Here, we call it I2. In other words, the current flows through 3K here is I2. The current flows through 6K, you also have I2, of course, as flowing upward, following you defined rotation direction. With this being said, look at the 6 kilo ohm. What is the voltage across it? In other words, what VA equal to? It equals to 6K times the current through it. The current through it is I1 and I2. So what we need to do is I1 minus I2 since they have opposite direction. Of course, why we are not using I2 minus I1? It is because, again, the passive sign convention. The VA polarity is positive on top, negative on the bottom. Therefore, it is fitting the direction of I1 rather than I2. So we are using I1 minus I2. So again, VA is equals to 6K times I1 minus I2. Third voltage term is very simple. Directly a voltage source, a minus 12. Well, we're gonna do nothing about it. Let's try the second equation. In mesh 2 KVL, what we have here, as we said, we have I2 going through 3 kilo ohm, I2 going through 4 kilo ohm downwards, and I2 going through 6 kilo ohm upward, like this. So how to rewrite them? First, V2 here is rewritten to be 3 kilo ohm times I2, as we said up here. Passive sign convention again. I2 entering the positive polarity of V2. Okay. Second, VB is equals to what? VB is the voltage across 4 kilo ohm. And again, you have a I2 going downwards through it, as well as a I3 going upward through it. So how to write this VB? VB equals to 4 kilo ohm times the current. And the current should be I2 minus I3. Since the polarity of VB is like positive up here, negative down here, fits the current of I2. not I3. Last one is the VA in this equation. So VA is here. We have rewritten VA here in previous equation, so we just copy it down here. So minus VA here, minus VA here. Then let's see the last one. In mesh 3 KVL, V3 equals to what? V3 follow the same idea. I3 times 9K. Perfect. VC equals to what? VC is the voltage across 3 kilo. It's simple. You only have I3 flow through it. Nothing else. So 3K times I3 as well. Last one, minus VB. So VB itself equals to what? We have rewritten it in the previous equation here. So we just copy it here. Minus VB. So this is how we rewrite the KVLs into so-called mesh analysis equations. So in the exam, again, remember, what we need is such equations rather than these equations. So from these equations, let's count how many equations and how many unknowns. We will find both numbers are 3. So we're all set for the algebra. We find the 3 mesh currents, I1 through I3. Okay. So I1 obviously is also this branch current. I2 is this branch current and here current. I3 is current through here. So be careful. None of I1, I2, I3 is the current here and here. So what is the current through 6K and 4K respectively then? If you're defining the current through 6K in downwards, then what is the current through it? It should be equals to I1 minus I2. Similarly, if you define the current through 4 kilo ohms downwards as this, then the current through it should be equals to I2 minus I3. So this is something a little bit tricky. Might cost you some time to digest. But again, I1 is the mesh current through 9 kilo and 12 volts. However, it's not directly equals to the current through 6 kilo. And same thing for 4 kilo. And I3 is the current through 9 kilo and 3 kilo. I2 is the current through 3 kilo. From these currents, we move to the voltages. So obviously, we can easily find the V1s, V2, V3, and VA, BC by applying Ohm's law. However, none of these voltages is the node voltages. What is meant by node voltage? Node voltage we have learned from previous nodal analysis. This V1, well, we called V1 in nodal analysis. However, here we might need to redefine with different name, maybe Vx. At this node, what is the voltage with respect to the ground? And this is another node voltage, maybe Vy, with respect to the ground. Vz as third node, Vx1 as the fourth node, and the bottom node we know is 0 volts ground. Right? So Vx remaining as 12 volts because of the 12 volt voltage source. And then how about Vy, Vz, Vx? How we find those? Well, here you need to be careful. For example, how to find Vy? We need an equation. So how about Vx minus Vy equals to V1, which is already calculated as 9 volts down here. And then of course you know Vx is 12. We already got it. From here, you can easily find Vy, which is the voltage at this particular node. I leave V2 and Vx1 as exercise for yourself, and let me know if you have trouble of finding them. And obviously, you should end up with same node voltages as in the previous nodal analysis. With a couple of examples, I hope all of you guys have a rough idea about these two techniques. And again, they are the core of this course. And a little bit more here about them. So nodal and mesh are alternative techniques, and they are systematically find any voltage and any current in the circuit you want. However, again, be careful which one the problem is asking for in the exam. Okay, not all of them. And next about them, so the previous voltage current dividers we learned from module 1, and equivalent resistance we learned module 1 too. Those methods are also alternative techniques to conduct a circuit analysis. And this is how you summarize them in your mind. However, nodal and mesh analysis are able to solve any circuit without any constraints. However, the dividers and equivalent resistance, those techniques are not necessarily. They do have constraints. For example, when you try to apply dividers to solve a circuit, you have to see only one single independent source. More sources or having dependent sources? No, you can't apply voltage or current divider directly. Similarly, if you have more than one independent source, you can't apply equivalent resistance technique either. So by all means, nodal and mesh can do everything you want for a given circuit. Well, that's why it is the core of this course. You want to keep something, learn something out of this course at the end of the semester. Here are the things. Module 2, and inside of it, nodal and mesh. Here I'm showing 3 examples to explain this very last point, from where you can't see clear voltage divider, current divider, or equivalent resistance you can do. Therefore, don't think about them. Instead, straightforward step into nodal and mesh.